In this video, we'll introduce RL circuits, which are very similar in concept to RC circuits. However, since an RL circuit is going to have us look at the currents through the inductor rather than the voltage across the capacitor, we'll need to use slightly different methods of analyzing them. We're going to start with RL charging rather than RL discharging. And what I'm going to do for the derivation is make a lot of assumptions. The reason I'm going to do that is because a lot of the concepts have been discussed in the RC circuits. So discussing them again would just be repeating myself. So let's go ahead and draw the circuit. Once again, we have a switch. Always will have a switch. And it's closing the switch at t equals 0. Now, in the way this is drawn, I'm interested in I of t through the inductor L, charging through the resistor R. I'm going to make one very important statement. I of 0 has to equal 0. There's nowhere for current to flow when the switch is open, so we don't need to worry about the case that I of 0 might be non-zero in this particular circuit. In RC circuits, we use KCL. In an RL circuit, we should be using KVL. So going around the loop, and we'll go around that way, we have negative V plus R I of t plus L di by dt is 0. And hopefully, what you'll notice is that this is very, very similar to what we had with the RC circuit, except we're dealing now with current. If that's the case, we're going to assume an expression for I of t that is of this form: k1 plus k2 e to the st. Once again, we need to know k1, k2, and s. Without too much derivation, I'll just tell you that s is actually going to be given in terms of R and L. In particular, S is going to be negative R over L. But what are K1 and K2? Once again, we use our initial conditions and our final conditions. Our initial conditions we know, so let's start with that. We know that I of 0 must equal 0 because the switch is open, and that'll be equal to K1 plus K2. So like with the capacitor, K1 is negative K2. Now, we need to use our final conditions, FC. And I'm going to make a claim that we'll talk about. I of infinity equals V over R. Why? Let's take a look. Remember, for an inductor, the voltage is L di dt. So, and remember that's voltage on the inductor. If di by dt is 0, then VL is 0, which means our inductor acts like a wire. It behaves as though it's just a regular wire, no voltage across it, passing current through. If that's the case, then when I redraw this, after a very long time, that's the circuit I get. And the current in it is V over R. Now you might say, why is it that our inductor just becomes a wire? Well, keep in mind that V is a constant DC voltage source, so its derivative is 0. The only thing inducing a change in this circuit is the inductor. However, we're dealing with a transient effect. If the inductor didn't have these transient things, if they kept on going forever, then we'd have a very different discussion. However, it would mean that the inductor has to produce energy in the circuit, and it cannot do that. So, if I infinity which is another way of saying I at infinity, is equal to K1, because remember S is negative R over L, is V over R, then K2 is negative V over R. And therefore, our expression I of t through the inductor is V over R minus V over R e to the negative R t over L. Sometimes we'll call the expression L over R as tau, just like we did for the RC circuit. However, to avoid mixing up more notation, I'm not going to do that.